So friends, we are all learning on prognostics and health management systems approach. Uh, the approach that we are discussing, there are some new elements of prognostics and elements of health management in the context of systems approach. Okay, and then now we have in last two lectures we have understood the topic. It's a context. In the second lecture, we understood the type of learning mainly and associated subjects. And now we will discuss the probabilistic methods in machine learning. At the outset, I will tell you the probabilistic or statistical approaches. They have two categories. One is parametric parametric approach, and other one is non-parametric approach. So in this lecture and next lecture, we will be discussing the parametric approaches. Parametric approaches means distribution, as I mentioned earlier, for data treatment and analysis. And non-parametric means wherever distributions are either not available or you require effort to understand which distribution it is close to. So that kind of system that will be discussed. So let us first talk about in lecture 3 and 4 the probabilistic methods, that is statistical approaches. So first we will discuss just in one slide the reliability matrix, because any system we develop, one is the reliability as input and other one is testing and its validation, how good that tool is. Reliability matrix is required. And then probability distributions, they are the core subject of machine learning. And there we have two classification I would say: continuous distribution and discrete distribution. And in continuous distribution, that is it is called normal or Gaussian distribution, we will be discussing standard normal distribution. It has got a very special context when we talk about the machine learning as applicable to ANN or deep learning. Then we will be also discussing about the central tendencies. These central tendencies, standard deviation, and many more features. When we talk about the vibration signature and all that, they are basically Curtis's value. They are basically they form part of actually feature extraction. So, and then of course regression analysis, how well the data is agreeing with our decision or our line which we are projecting for future use. So regression analysis is required. But here in this lecture, regression is a subject in itself. So here I will be giving introduction. When the opportunity available in the future, I will be discussing in more detail. Otherwise, this itself will be sufficient for the purpose of machine learning algorithm. So reliability is one of the important characteristics. Safety and reliability, these two are characteristics which are very important. That means risk should be to the acceptable level. There is always acceptable. Without a risk, there is whatever aspects we are dealing, there is a but the component is so low. Like I'll give you one example. The elevators, people were in the 50 years, 60 years ago, some old age people, they were not using elevators because they found there is a risk associated with the elevator. Now present generation, they have understood in the context that elevator, even though accidents keep happening about the elevator, but we take it as an acceptable risk. So aviation, flying in aircraft, we without any thinking, we take the flight, board the flight, complete our task and come back, because always there is a comparison between benefit and risk. So if benefits are amount very high, then probably we can take the risk to our side. So that is our, and then reliability, yes, it is the benchmark of production, benchmark of our we are doing well, our state of the art developments, tools, methods. So they are very important, and they are basically provide the bottom line, for the business. So operation of the plant is very necessary, but safety is or risk is a overriding factor. Risk reduction is a overriding factor. So you would have seen since 5-6 decades, when the actual reliability methodology came, or mean time to failure and mean time between failure were two benchmark which were considered as part of reliability characterization. And the one was availability. Plant availability means continuous availability of the plant. Reliability means any interruption, no interruption should occur during the mission time. So it is called reliable. If interruption occurs and number of interruption occurs during that mission, then reliability goes down. That is what is. And then frequency of events. Reliability is one thing, and frequency of events means undesired events, because those undesired events, they first destabilize the plant. It takes the plant from one state to another state momentarily, and if not managed properly, then it has a potential to deviate to unsafe state. Okay, the plant systems are redundancy, diversity, 99.9999%, they bring it to the safe state. That is because of design actually. So reliability characteristic, we know just for the sake of showing, R for a mission time is equal to exponential minus lambda. Lambda is a failure rate. Okay, so and we also know that reliability of a component in continuous operation comes down over a period of time. Why? Because of wear and tear, or it could be because of some. So what we do to overcome that situation? We do maintenance. So reliability comes to theoretically to the original level, and that is very simple. So it has got direct implication in maintainability. Okay, but the limitation of this reliability estimate is it is probabilistic in nature. It will give you probability of 10⁻³ 10⁻⁴, and that is where there is a comparison with the prognostics and health management. That means prognostics and health management, prognostics rather, it gives epoch of time and management action can be performed. So probably you will find that PHM with advanced tools and technologies availability and improved model and methods, they will overshadow this traditional approach of reliability estimation. Of course, it will have its own place, because finally I need some tool for identifying, characterizing, or prioritizing my system so that I can do maintenance management and all that. But then for that is there it is applicable. But when it comes to real time plant management and all that, in a control room like a situation, prognostics and health management is going to be the one of the biggest tool, because it is giving me remaining residual useful life, and then I know whether it is 1 day, 1 month, 1 hour, 10 minutes, how much it is. So I can take, and even if it is 10 minutes, I can take safe actions. Actually, there is no problem. Actually, so this is about the reliability now. So this is the reliability metrics, and we have to see, and risk also, because we are calling systems approach, and in systems approach, probabilistic risk assessment is the methodology that provides solution for real time scenario, what should be done for what, and what happens when system is not in reference state, and when happens when we take the action and it bring it back to the normal. So all those things part of, so that form part of management decision making. Now just let's take an overview actually. this we have not discussed in a one table or so different type of distributions because later on we will be talking about them whether it is continuous or discrete distribution. Okay. So, let us say the most popular one is normal or Gaussian distribution. It is basically a two parameter distribution, mu and sigma. Mu is mean and sigma is standard deviation, and this is called probability density function ft. F is a function of time, and it's a plot. You can see how it is a bell shaped. Normally it is called even bell shaped distribution because it has symmetry on both the sides of the zero value or mean value. So, mean value certainly will come here with the maximum frequency, it will come here for normal distribution, and so PDF is on the y axis and x is there or t is there on this x axis, and the distribution is 1 upon under root 2 pi. Actually, this, if I remove this t, this is for log normal distribution, t if I remove here, and mu, and if I take the function t minus mu square is become normal distribution. Okay. So, because otherwise these two will look like same actually. So, okay, it is a good comparison also, you can see here. You saw that normal distribution and log normal distribution, there is a very minor difference, you know. Minor difference is what? If it is a log normal distribution 1 upon under root 2 pi, sigma into 2 pi, t is not there, okay, for normal distribution. Exponential minus 1 by 2, and instead of len, it is the parameter t minus mu divided by sigma whole square. Okay. So, it is sort of, you know, we are able to understand here itself what is a log normal distribution and log normal distribution, otherwise they both look like same actually, you know. So, this is log normal, this is with a t removed here, it is you know, and exponential minus not len t, it will be simple t here, t minus mu divided by sigma, and this t minus mu has got a significance we will see sometimes in the standard normal distribution. Okay. And then we have exponential distribution, single parameter, it is lambda, failure rate. Okay. The way here it was mean and sigma, it was, here it is lambda, failure rate, and the probability density function ft for this exponential distribution is lambda into exponential minus lambda t, okay, and single parameter. Okay. And the way it was a bell shaped here, this is not a, it is a failure rate is constant over here. You can see it is ft is reducing, but failure rate is constant. So constant. So it is called constant failure rate. Okay. Reliability, availability analysis, it is used. Here this is used in production system. How the shaft diameter varies, definitely it will vary around the specified value 5.6. So, it will move around both the sides in terms of dimension, shaft diameter, length of the component. So, normal distribution is suitable there, but here it is a reliability and availability study it is used. Then Weibull distribution. Weibull distribution is 3 parameter distribution, but even Weibull also, if we remove the location parameter theta, then alpha and beta that we have here. So, it becomes if I have to talk, this is a 3 parameter I have shown here, but if I have to talk about the 2 parameter popular Weibull distribution, it will be like beta upon alpha x upon alpha raised to power beta minus 1, theta will go off here also, exponential x upon alpha raised to power beta. So, even though I have shown 3 parameter Weibull distribution, actually 2 parameter Weibull, because location parameter is normally ignored. And the beauty of Weibull distribution is this, that you know here itself on ft scale it can show our cumulative whether it is a, if it is showing like this, that is 3 or 4, that means ft is then it is like a normal distribution, you can see here. Same Weibull distribution, if the shape beta parameter, because beta is called shape parameter or slope parameter. It is called exponential normal distribution. When it is beta is equal to 1, then it is exponential distribution, like here what we have here. So one distribution, if we have some data, if you want to, and now Weibull has become a subject in its own. So Weibull distribution, Weibull plot graph. If you plot our data, and if the gradient of the line, that is tan theta, which is a manifestation of beta value. If it is 1, it is exponential distribution. If it is 3 to 4, it is a normal distribution, and many more variation of this factor has potential to indicate other distribution also. So it is called sometimes even a universal distribution also. Log normal distribution. Now, where log normal distribution is used, when logarithm of the random variable or data it is normal, then it's called log normal. So here you can see ln of t we have taken here. Instead of mu t directly, we have taken mu minus mu sigma, and here sigma and t both will come here. So so you understood now a log normal distribution, that I don't know whether you are able to see, it is skewed on one side. Like here it is a bell shape, it doesn't look like a bell shape. It will have some inclination on this side, and that is the left side, and again it will come down. So in a open literature there are many shapes have been shown. Log normal has got a skewness either this side or that side maybe. You can reference to more literature. And the biggest advantage, like in probabilistic risk assessment, the error factor is generated from here, and that error factor is like uncertainty in the associated with the component. So this distribution is very useful. If I have to simulate my fault tree, then I'll use the mean value and I'll use the error factor. So that means variability in the data or uncertainty in the data is reflected at component level. And if I do the Monte Carlo simulation, so exponential distribution and log normal distribution. Log normal distribution for the component, and for giving the failure probability, it is the exponential distribution. That is, in failure probability means cumulative FT, which is varying from 0 to 1. So that failure probability, or even reliability. Reliability also, the popular model that I showed you, it was an exponential distribution model. Okay, so this is about continuous. There are many continuous distribution, but in risk analysis and for systems approach, I think if you know normal, exponential, particularly exponential, Weibull and log normal. Why? Because Weibull distribution is used in life test, which is central to one is trying to understand the difference and modeling the time to failure of the component. So like we are saying, remaining useful life. Even remaining useful life estimates are also made by testing the component at higher stress level, and using Weibull distribution we try to understand their characteristic life, okay, and beta value, and that input is utilized for even labeling our physics of failure models. Okay, so normal distribution is not used, but sometimes variability. Normal distribution, the main problem is it is so complex to be used in practice. So that is why we have the standard normal distribution. People have found, or our researchers have found, to answer this complexity by making T minus mu upon sigma is equal to Z, and making it to standard distribution where mean is 0 and sigma is 1. We'll see in next few slides what is standard normal distribution. But before that, let us see what is discrete distribution, where the outcome is in numbers, not continuous. It is not continuum of value 1.2, 1.5, 1.35. No, it is discrete. 1, 2, like a machine number of diesel generator failure in a year. It cannot be 1.5 or 2.5. It will be 1, 5, 15. So they are discrete values, integer values. So that's why it is, these are called and for us most relevant ones are Poisson distribution and binomial distribution. So Poisson distribution, rho is the characteristic failure rate, So this again becomes a single failure. So probability of desired variable x is equal to rho x. X is the parameter of interest, exponential minus rho upon factorial x. It's almost approaching like an exponential distribution, because here also like lambda, it is rho is a lambda t is a parameter that we are taking into account. Okay. And then assessment. So this distribution is very useful where we are seeing frequency of events like number of defects in the pipeline, a number of buses coming to the bus station or train station every day or every hour, and we are trying to understand that data. Then this kind of distribution, that is Poisson distribution, is very useful. Assessment number of failures in a given time, or the defect frequency in across the length of the pipeline and all, we use Poisson distribution. And binomial distribution we use where it is like combination, permutation combination mechanism. I have my 9 safety devices or 20 safety devices, out of which even if 5 devices they actuate and make me safe, so I'll do analysis of 20 out of 5, what is the probability, and that probability, whatever figure is there, I'll see that whether it is in the acceptable region or not. So this probability of x, that is let us say a combination of 11 out of 3. So n is 11, x is 3. What is the probability of n? So the probability of success. Okay. So if I success is x, then it is here, that value will be there, and this probability has to be estimated separately, whether it is success or, and 1 minus, if it is a p is success, 1 minus p is a failure, n minus x is again a failure rate. So we have to characterize this probability of failure. If we say, then probability of failure when 11 out of 3 whether what is the probability of 3 failure out of 11. Okay. 11 is the number of devices. Okay. So probability of failure we know is probability of x, that you have to find out by separately. Let's say we had our record shows there were p number of failure out of 120. So that will give me a probability, and x is the probability of failure, 1 minus p is probability of success, and that's how n minus x is the other event. It's a operation actually. So this is a binomial distribution is used for combinatorial logic actually, assessment of combinatorial event considering in the space actually. Now, as I mentioned you, if I have to estimate the failure probability if as a function of time, then this distribution, now for you it is very simple. You can replace this distribution in your normal table is there in your table. So this is actual normal distribution. It is better you can make this observation. Okay. So the subject is standard normal distribution. Why we do it? Because computation is very easy. The cumulative distribution function for normal distribution can be written as a, but the challenge is evaluating this integral from minus infinity to plus infinity, because normal distribution it can be both the ways actually. So minus infinity to plus infinity, and ft, cumulative density function. So integrating this small ft value and 2, it will become 1, So that will be cumulative. So it varies from 0 to 1. So 1 upon 2 pi, 2 pi under 2 pi minus. So it is very difficult. So very innovative solution was found out that convert this particular whole thing into a standard normal. That means replace this term here, t minus mu upon sigma. So here t is a random variable. So So T minus mu upon sigma, you replace it here. So you get this distribution exponential minus 1 by 2 z upon 2 square dz, and this value is available in the table. So if you see normal table, you will find this value. So if this is a normal distribution, this is a standard normal distribution. How? Why? Because mean is 0. We have put mean 0 here, okay, and standard deviation 1. So then it goes plus minus and all that, and it is very useful in probability theory. So to get a better understanding, we have this example for you, and you can see this is a normal table over here, normal distribution table. Okay, so this has solved all our problem, that complexity of normal distribution. Okay, so let's take a small illustration. We have a problem. It was reported based on the data collected from the market survey that mean time to failure of the subject non-repellable component, I am not naming any component because it is basically for understanding, is 5,700 hours. So mu is 5,700 hours. The standard deviation for this data was evaluated to be 450. So that data is also available, and then it was indicated that the data follows normal distribution. Estimate the probability for the product that the product will last less than 400 hours. When we go to a shop, we say if it will not fail in for at least 4,000 hours, no. So that means what we are worried about is what is the probability that it will fail in 4,000 hours. Okay, so that is what the question is, and like a customer, we have formulated this problem. Z is equal to T minus mu upon sigma. We have a value of T 4,000 minus 5,700, 1,000 divided by 450. We got a Z factor of 2.26. Now Z values are given over here. Okay, and when we have the Z values there, looking at the problem, negative part of the normal curve can be omitted. Okay, so the probability of failure of less than 4,700 failure less than, it should be 4,000 because our value is 4,000 here. In 4,000 hours is probability 4,000, you know, and then it is 0.0132. Okay, so this figure is 4,000 here. Okay, and then probability of 4,000, it is 0.012. The probability of failure is estimated before 4,700. So here we get the probability is like is very low, that it will fail before 4,000, or we can do a re-estimation also of this problem, and that's how it is. So what I am saying is Z value you will get here, and if there is this is 2.22 and we have to see which we have to go here, we will get a value here, and that value you have to simply put it here. Okay, so between 0 and 4,700 is 0.0132, which is a low probability. Okay, so that's we get the quantitative answer over here, and use those curves. Many shape of curves are there, but here we are talking about this area. Okay, this area we are talking about. So be careful when you using any log normal distribution. We are talking about the area which is there for a Z value of 2.22. Okay, it's like this here, and we are taking the right side of the area into our consideration. So while using the log normal distribution, see what we are doing, which side, and which side represents our problem that we are doing. But we have understood from this standard normal distribution example that normal distribution, and we without dealing with the complexity of the integration and all, we could through this support system, that is table, we are able to get it, and now we can computerize this whole thing. So automatic answer will be available to us every time we wanted to do that integration. Now one more thing, we talked about mean and all that, because central tendencies are very important for as a feature extraction or feature of the data. So we know that mean is very simple. Add all the elements, summation of all the elements divided by the population size, that is n, you get mean. Mean of data is 18.2 in second column. Okay, so here we are getting 18.2 mean for the data. Now I have used the same data and then I have provided the mean. Now arrange for median value, we have to arrange them in the ascending order. Okay, median I have arranged the value, and how median is we get the select the middle value. Okay, so select the middle value, and middle values are 2 because these numbers are even number. So 2 value 18.5 median, because here the idea was to give whatever feature from the data you want to give, and which one you want to select to represent your population should be known. And the mode is number with maximum frequency is called. So here 20 is the frequency, so mode is here there. And so that means the mean, median, mode. Mean is average of this, then median is arrange them in ascending order. Okay, and take the middle value. If one value is there, that means equal number on this side, equal number, but here equal number will become this side when you take 18 and 9 2, so 18.2. And then mode means frequency of value, whichever event is showing more frequency, that becomes the mode. So now let us see how it compares when you have a distribution function and when you are plotting it here. So mode is the frequency, maximum frequency, so obviously it will come here at the center, and then median value will be having here after that, and mean will be somewhere here actually. So on normal, mean and mode and median, they all overlap. Okay, because this is central value also, this is the maximum value also of the frequency, and this is average value also. But if it is a normal distribution, and in normal distribution the emphasis is there to use median. Okay, because frequency can be varying, but median you can rely more. It comes on based on the average. It comes based on the central tendency, that is mean value, central value. Okay, so you can take it as a heuristic that for log normal distribution we are always interested in the median value, because that gives us a sense of that data is data or the area is both the sides are sort of equal. So this we have understood what is the significance of normal distribution, log normal distribution in respect of central tendencies. Okay, now just I wanted to give you a feel of regression and all that. So we had power failure data. So let's say we have power failure data, and how we can use a meaningful evaluation. Data has been first. The data was the power failure data here. Here it is given from beginning and all, and now we have to arrange them in ascending order. You have to give a rank, and then finally what you will find that it is approaching 1. Okay, so and that rank can be evaluated between using this formula I minus 0.4 divided by n plus 3. So I means individual event and n is total number of event, and that you get a fraction here at the beginning, and finally it approaches 1. So if I plot this data, grid power failure data, and if I draw a line here, okay, now I want to find out how well this line represents the data. So I had to do a regression analysis, and either you can do it on computer or you can plot the data for yourself and use a regression algorithm. So regression analysis will determine R square. R square is called coefficient of correlation. This graph I am showing you, whenever there is a regression thing, you will find in the different context we are trying to understand agreement between two data or a line and data and something like that, because we want to know whether whatever we have chosen that represents the reality or not. The R square value is above 0.9. That means the data follows exponential distribution. So I have plotted this data on exponential distribution. If it is 0.9, R square value is 0.9. Maybe I'll tell you separately in a lecture how this R square is evaluated. We'll go from fundamentals, X and Y distance and their model and all, and we'll estimate it. I think I'll do it. But here the objective was to give you a sense of inference, how we can draw from a line and data, and whether they are reflecting or they are in agreement with each other. Otherwise, we can draw a line. Consider what happens. We have data only. I could have drawn this line like this also. Okay, I could have drawn the line like this also. So whether I have drawn this line correctly or not, that will depend on distance between this line and the data, and that will come or we'll understand only when we discuss separately how the regression is done. But you should know that the coefficient of correlation, or R square, is 0.9 and above, then the data is in agreement with the line. This is a heuristics actually. So in this week, we have discussed probability and statistics. We have discussed distributions also, and we to some extent discussed applicability of the distribution also, where exponential distribution is used, where normal distribution is used, and for risk assessment which are the relevant. In fact, we have not discussed all the distribution, but we have discussed important distribution. What we call it is a systems approach. In fact, one more distribution which we have not discussed here, but we saw in some form, that was a Poisson distribution. Poisson distribution separately also I have elaborated. So this is going to happen in this course, that some of the things we are talking in the beginning, but as the need arises, like distribution, we will be showing you the new application, and that way it will have a good spectrum of any topic or subject that we have here. Central tendency, we mean, mode, median, and what is their significance, that probably you would have understood well. And regression, you can see it was an introduction only. And what we did was, we have plotted the data, and then fraction, we have normalized value we have taken, and finally we are trying to understand whether the data, whether the line is representing the data. So this is end of lecture number 3. Now and this is part A. Part B in next lecture.